Hi, and welcome to the Westcliff University podcast, where we explore revolutionary ideas that force us to rethink life, creativity, humanity, and the future. Today, I've got the privilege of interviewing one of the best-known biomedical gerontologists on the planet when it comes to aging and longevity. We're about to dive into one of the most provocative and consequential questions of our time. Can we cure aging? And not just slow it down, but actually reverse the damage and outpace it altogether. Aubrey de Grey has spent the past 2 decades advancing the idea that aging is not inevitable. It's a disease, and like any disease, it can be treated, managed, and potentially cured. But before we dive in, if you'd like to learn about Westcliff University, including our incredible undergraduate athletic program, visit westcliff.edu. You can also connect with us on Facebook, Instagram, LinkedIn, TikTok, X, formerly Twitter, YouTube, and the Little Red Book. I'm Dr. Barry Sandrew, your host on this journey. The views and opinions expressed by guests on this podcast are solely their own and do not necessarily reflect those of Westcliff University or the podcast host. Any medical or medicinal information discussed is intended for informational and conversational purposes only. Claims regarding health or wellness benefits are the personal and/or professional opinions of the guest. Listeners are encouraged to consult with a qualified healthcare professional before making any medical decisions. Now, let's get into it. Aubrey de Grey is the Chief Science Officer of the LEV Foundation. That's the Longevity Escape Velocity Foundation, where he's leading a major push toward what he calls robust mouse rejuvenation. Yes, he's trying to make mice live a lot longer. Now, this is a prelude to full human rejuvenation. He believes we're just a few years away from a breakthrough moment that could ignite a global movement to end aging as we know it. His TED Talks have millions of views, and despite skepticism from some in the scientific community, his work has helped shift aging research toward intervention-based approaches rather than merely studying the aging process. Whether you're skeptical, curious, or ready to sign up for year 200 of life, this conversation will challenge what you think you know about aging, medicine, and the future of being human. So, join me in welcoming Dr. de Grey. Hi, Aubrey.
Hello, thanks for having me.
Yeah, this is a real pleasure. You know, you're one of the most recognizable thought leaders in the world on longevity, and I appreciate you taking the time to meet with our Westcliff University audience. In your book, your 2007 book, Ending Aging, you outlined a controversial yet influential thesis that the first human who will live to 1,000 years may already be alive today. Do you still feel that way?
Certainly I do, yes. And in fact, it's quite frustrating and surprising to me that most people don't really appreciate the logic of how I arrived at that conclusion. Because the conclusion arises from a concept that I coined 20 odd years ago called longevity escape velocity, which basically says that once we have postponed the health problems of late life by 20 or 30 years, we've done the hard part. Essentially because the way we will do that is by not slowing aging down, but by reversing it, by making people biologically younger again. And every time we do that, we essentially buy time for scientists to figure out how to do it the next time, 20 or 30 years later, so that we can, stay one step ahead of the problem. And it's really pretty unarguable and pretty obvious that 20 years is quite enough time to get the next 20 years of life, just once we've figured out how to get the first 20. So I find it quite paradoxical that this is still such a controversial idea, even though the specific ideas that I've been putting forward for getting those first 20 years of additional life have now become broadly accepted. That was controversial as well when I first started talking about this 25 years ago. But I kind of won that argument scientifically. And yet still, the concept of longevity escape velocity is quite aggressively resisted.
Could you explain that for people who still see aging as natural and unavoidable? You've got some slides, I think, that might explain that.
Sure. In order to explain to people why aging is a phenomenon that has the potential to be brought under medical control, I have to start right at the beginning. I have to disentangle and dismantle a lot of interlocking misconceptions that people have. And I like to start by talking about things that we already do know and understand. And here's the first one. The fact that 200 years ago, more than 1/3 of babies would die before the age of 1, even in the world's wealthiest nations. And we fixed that. We fixed it, really thoroughly. Hardly anybody dies in the industrialized world before the age of 1 anymore. And we did it, of course, by really simple mechanisms, by figuring out that hygiene is a good idea, by the, really first steps towards modern medicine, vaccines, antibiotics, even just, mosquito nets. So the big question that we can start from is, what is so different about the health problems of late life that has made them resist this approach? Why haven't the same kinds of medical interventions that work so well early in life, why do they not work late in life? Most people think that the answer is quite simple, that it is just that there's so many things that go wrong late in life. Of course, you're not supposed to be able to read this slide. The idea is simply that there's so many things that go wrong and they interact with each other and exacerbate each other. The sheer complexity is too much for medicine to handle. And that is part of the answer, but it's only a small part of the answer. The main answer, the main reason why we haven't made progress is because we've been going about it in really an unintelligent way. And the reason we've been doing that is because of a failure to define aging appropriately. If you ask most people, in what ways can somebody be sick? The answer they will give will look something like what you see on this table. They will say, well, you can get sick from infections, that's column 1. Or you can get sick from choosing your parents unwisely, from inheriting things that make you sick. That's column 2. Then there's the big one. You can get the chronic progressive diseases of late life, such as Alzheimer's or almost all cancers or heart disease and so on, all the things I put up in ridiculously small print a moment ago. And then most people will say that way out in the stratosphere, there's this fourth type of way to be sick, which is aging itself, which consists of these rather poorly defined phenomena like frailty, and people think of it as completely different from all of these types of diseases. So different that, it's kind of implicitly off limits to medicine. And it's just like built into the fabric of the universe in some way. That's what I'm denoting by that big thick black line. But that's completely wrong. And in order to explain why it's completely wrong, I want to start here with my definition of aging. There's lots of definitions of aging out there, and that's a problem in itself, right? That people talk past each other because they define that word in different ways. So I want to emphasize that this is a definition which is not controversial, but it may be stated in different words than most people would. And the good thing about this definition is that it demystifies aging. It shows how we should think about aging in a manner that demonstrates that we do essentially understand what it is already. Aging is simply the combination of two processes that you're seeing here. There's a left-hand process which goes on throughout life, even starting before we're born, in which our metabolism, which is to say the network of processes that keep us alive from one day to the next, generates damage. Now that damage means that the word damage here denotes a whole bunch of changes to the structure and composition of the body at the microscopic level, the molecular and cellular level. And the reason I use the word damage to denote those changes is because they are progressive, they accumulate throughout life, and the body is only set up to tolerate a certain amount of those changes before things start to go wrong. And that's, of course, what happens in the right-hand process I'm showing you here. Late in life, we have more damage than that threshold level, and that's when we start to see decline in mental and physical function. Those declines are what I'm denoting by the word pathology. And of course, they get worse and worse, and eventually they kill you. So that's aging. It's just those two processes, really, really simple. But that really helps us to clarify some of the things I've already been speaking about. Here is a corrected version of the table I put up a couple of slides ago. And if you look closely, you will see that all four of the columns are exactly the same as they were last time. The only thing that has changed is the location of that big thick black line, which used to be between columns 3 and 4. So what does the relocation of that thick line mean? It means two things. First of all, it answers the question that I began the talk with. It's not surprising that the same kinds of medicine that work so well on column 1 do not work on column 3, because they're completely different kinds of phenomena. Column 1 consists of things that have an external source that you get infected by. Column 3 is intrinsic. It's a consequence of being alive. But perhaps even more importantly, you have another thing that's denoted by the relocation of the black line, namely, it shows that there is no meaningful difference between column 3 and column 4. Honestly, there really is only a semantic difference. Column 3 is the aspects of aging that we've chosen to give disease-like names to. That is all. And that helps us enormously, because no one's going to tell you that the things in column 3 are off limits to medicine. So therefore, the things in column 4 are not off limits to medicine either. That's a really important thing to get one's head around. Why does this all matter? Why have I spent so much time belaboring the definition of aging and the mistakes that people make about ways to be sick and so on? The answer is because those mistakes underpin the mistakes that we have made in trying to do something about aging. So here's my definition of aging again, and we can talk about what it means to do something about aging. What it means is simply to separate metabolism from pathology, to allow people to stay alive, in other words, to continue performing metabolism without getting sick, without exhibiting the pathologies. And there are various ways one might do that. One could try to separate metabolism from pathology by separating damage from pathology. And that is what we try to do these days. The overwhelming majority of the effort that we make to keep people healthy late in life consists of how we do that. And that's what I'm calling geriatrics. But we can see from everything I've said in the past few minutes that that's a complete non-starter. It's absolutely ridiculous, because the damage is accumulating. And therefore, anything that, addresses the consequences of damage, the pathologies, is going to become progressively less effective as the damage continues to accumulate. It's so obvious. The complexity aspect that I mentioned earlier is a problem, but as time goes by, we get better and better at coping with more complex things, so that shouldn't be a showstopper. But the fact that this is simply targeting too late in the chain of events, that really is a showstopper. Geriatric medicine will never work to keep people healthy late in life. Now, I'm not the first person to think of that, to realize that. More than 100 years ago, a few people started to realize that geriatric medicine was a mug's game. And they said, well, okay, we want to separate metabolism from pathology. They wouldn't have used exactly these words, but they would have essentially said that. Maybe we, instead of doing it by separating damage from pathology, we can try to do it by separating metabolism from damage. In other words, by essentially making the body run more cleanly, slowing down the rate at which metabolism generates damage. So this was inspired by the living world. The living world obviously exhibits, different species have hugely different rates of aging. And so the idea was, maybe if we study that really hard, we'll figure out why that happens, why there's that variation, and we can translate that understanding into therapies. Unfortunately, as you may have noticed, that has also been completely unsuccessful. And this is why. It's been unsuccessful because metabolism is just too complicated, and the thing we don't want it to do, the creation of damage, is too inextricably intertwined with the things we need it to do to keep us alive. This is a simplified diagram of a small subset of what we know about how the body works, how metabolism works. And, it's already a nightmare. But of course, it's even more of a nightmare when you remember all the stuff that we don't know about how the body works, let alone all the stuff that we don't even know that we don't know. So, forget it. Not going to work. So, that's largely why by the 1970s, 1980s, people working on the biology of aging had basically given up. They had become rather like seismologists. You know, people who work on earthquakes, they understand that earthquakes are bad for you, but they have no aspiration at all to, stop earthquakes from happening at all. So it was like that. You couldn't mention intervention, actual, doing something about aging in a grant application back then. But that was premature because there is a third way in which we could separate metabolism from pathology. What we could do is not try to interfere with either of the two processes, but rather separate the processes from each other by periodically going in and repairing damage so that the overall amount of damage does not reach the threshold that kicks off the right-hand process, even though damage is continuing to be created by the left-hand process at the normal rate. What this does is it functionally sidesteps all of our ignorance about how metabolism generates damage and about how damage creates pathology, for that matter. You just need to know what the damage is, and that is all. And I call it the common sense alternative because, honestly, it really is common sense because it already works. We already do this successfully in other walks of life. Specifically, here's a car that's more than 100 years old. Now, you all know that this car was not designed to last 100 years. It probably had a warranty period of 10 or 15 years at the outside. And yet here it is working every bit as well as the day it was built. Why? Simply because of maintenance. Periodic, comprehensive, preventative maintenance. It just works. It wipes away all of the idea that, the machine has a warranty period. And there's absolutely no reason why the much more complicated machine called the human body cannot benefit from exactly the same thing. However, in order to drill down and actually, turn this idea into reality, we do have to make one more step. I mentioned earlier that we don't need to understand how damage is generated, nor how pathology comes from damage, but we do have to know what the damage is. And so what I did when I started thinking this way 25 years ago is I said, well, okay, let's try and classify the damage. Let's try and divide all the things we know that qualify as damage by this definition into a manageable number of categories. And that's what I did. And here are the categories on the left-hand side of this table. Now, you may ask, well, what's the point of that? What's the benefit from classifying a bunch of things? Well, fundamentally, the answer to that question is the right-hand side of this table. The fact that for each category, even though there will be many examples of damage within the category, there is a generic approach to addressing the category, to addressing all of the examples. So if we just take cell loss, the top one, as an illustration. Fact is, what cell loss is simply cells dying and not being automatically replaced by cell division. And we can fix that by restoring the number of cells using stem cell therapies. We just prepare cells in the laboratory into the right state so that we can inject them and they know what to do to transform themselves into cells that replace the ones that the body is not replacing on its own. And once you can do that for one or two tissues that lose cells, then doing it for the next one and the one after that is a lot easier because you can take advantage of all the knowledge that you have acquired by trial and error and so on in getting the first one or two working. And the same is true right down the list. So this list of 7 categories is something that I put forward, as I say, nearly 25 years ago. And you know what? It's standing the test of time. We haven't had to extend this list at all. Moreover, there's been progress in all of these areas to the extent that they're no longer in academia anymore. I mean, they are in academia, of course, but they're not only in academia. At least the more courageous angel and seed investors have felt that these things are close enough to prime time that they can take them into the private sector. Moreover, in academia, this concept has become mainstream now. Back 25 years ago, when I started talking this way, everybody thought I was mad. Nobody thought that I was saying anything useful or scientific, but I persisted and essentially won the argument. And So more than a decade later, a paper was published called The Hallmarks of Aging. I'm showing you two of the images, the figures from that paper here. And, it was the same idea. But by that time, its time had come. And sure enough, this paper is the Bible of the field now. It has been cited far more frequently than any other paper in the whole of the biology of aging this century, and I'm sure it'll stay there. So, that's pretty good news. I never have to justify this to experts anymore. But I still have to talk about it to everybody else, and that's why I'm here.
Yeah, thank you very much. I mean, so this pretty much kickstarted biomedical gerontology. Wouldn't you agree?
Well, no. I would say that it restarted biomedical gerontology. When gerontology began, as I mentioned, that was more than a century ago, it was perfectly fine to talk and think about actually intervening in aging. And that attitude persisted right through till the 1960s. It was only then when the field started to become more politically correct in an effort to get more money out of the government that people started to downplay the idea that aging was something we should try to fix with medicine. And they just kind of talked about it in terms of quality of life and so on.
Yeah.
And so there was this period of maybe 20 or 30 years of essential hiatus in the concept of biomedical gerontology. But it definitely existed in ancient history as well.
Well, so basically what you're saying is that lifestyle changes will lead to only a minimal amount of longevity. It really requires the repair of damage that's going to lead to a true longevity. I'm talking about 20 years or 30 years or beyond.
That's completely correct, yes. I mean, we can see this already, of course, because there are 8 billion, subjects out there who are pursuing a wide variety of differences in lifestyle and supplements and vitamins and diet and exercise and everything else you can think of. And sure enough, nobody has lived beyond 120 or so. And, that's not changing over time. It's not like we are consistently discovering new things that add another year or another 3 years here and there. It's just not happening.
Yeah, well, that would have saved me a lot of money in vitamin supplements for sure.
Well, I mean, of course, let's be clear. There's nothing wrong with small increments.
Yeah.
If you can do things that you don't find particularly, disruptive to your quality of life, then even if they only give you an extra 1 year or two of quantity of life, that may still make sense. So I'm not objecting to that, but what I have to always do is make sure that people don't think of it as the Holy Grail.
Got it. I mentioned to you when we spoke on the phone initially that a lot of leaders in AI today basically quote you and talk about escape velocity, longevity, escape velocity. But you've said that AI alone won't solve aging. What is the missing link that AI can't replicate?
Well, I mean, it's pretty simple, really. AI does not generate data. AI generates insights from data. So the goal here is to give ever-expanding AI prowess the substrates, the tools with which to help us to bring aging under control. I'm very sure that AI will play a huge role, but it can't work in a vacuum. You have to give it stuff. The best example that we have of this right now that perhaps illustrates this in concrete terms is a program called AlphaFold, which is quite famous because it was a program developed at a company called DeepMind that solved a problem that had been attempted to be solved computationally for decades, namely how to infer the three-dimensional structure of a protein, shape of a protein, from its amino acid sequence. And, so the two people who led that effort, Demis Hassabis and John Jumper, they got Nobel Prizes this year, so that's all very good. But one thing that they both said very emphatically is that the only reason they were able to develop AlphaFold, this program, was because of the grinding hard work of thousands of lab scientists, crystallographers, who used very laborious experimental methods to determine the three-dimensional shape of a few hundred other existing proteins from their amino acid sequence, and which were in a database called PDB, which was the starting point for AlphaFold. They said quite clearly, if it hadn't been for PDB, the AlphaFold could not have been developed.
And determining how they fold really can result in a lot of cures. Am I right?
Well, not exactly result in. It can enormously accelerate things. So, as I say, it's possible to determine the three-dimensional shape of a protein using crystallography. It's extremely hard work, very, very, very laborious. And now it isn't. Suddenly it isn't at all. So this is rather similar to the human genome. 20 odd years ago, the human genome was sequenced. That didn't enable us to do things in drug discovery that we were unable to do before, but it did make those things much quicker and easier to do, much, much quicker and easier. And that, of course, means you do get more cures out there more rapidly. So, yeah, this is an accelerator.
Mm-hmm. There's a lot of interest from this audience, this podcast audience, on Brian Johnson, who I believe you know. He's an entrepreneur Sure. and founder of Blueprint, and he sold that for $800 million, and he's been spending a lot of money every year to try to stay alive longer. Isn't that true?
It certainly is. You have the named a little bit wrong here. The company that he sold for $800 million was called Braintree. Its main thing was Venmo, which everyone's heard of course. So Blueprint is the name of his current thing, the vehicle within which he is doing all of this anti-aging stuff. Yeah. So yes, I know Brian pretty well, and he's quite a controversial character at the moment. I definitely very strongly feel that his contribution to the field is a net positive, but I definitely don't think he's doing everything right. He, as you say, is a wealthy individual, and he is spending, so it's said, about $2 million a year on not dying. But I don't think he's spending it very optimally. I do not think he is minimizing his own chance of dying, let alone anybody else's, by his choice of priorities. He is doing one thing absolutely right, namely he is focusing very, very, very strongly on measurement, on understanding the impact on his body of the various things he's doing. And therefore he is in a nice tight learning curve loop, if you like, of understanding what works, what doesn't work, and optimizing for himself. Sometimes he says he's a little bit over general about things he's doing. For example, he talks a lot about sleep. I think there's no question that adequate amounts of sleep is absolutely vital for anybody's health. But he goes further and he says that sleep schedule matters a lot. And I'm quite sure it does matter a lot to him. He actually literally had for a long time a hard and fast rule that he would never take flights that went beyond 2 time zones because he didn't want to disrupt his sleep schedule. But I don't think that's true. I think that with other people, and I'm an example of this, the sleep schedule can be wildly disrupted for a day or 2 or 3. And as long as the overall amount of sleep is adequate, there's no problem at all. So your mileage varies depending on what, on everything about your metabolism, all the little details. And that's something that perhaps Brian should emphasize more. However, the main thing he's getting wrong is he's not looking forward far enough to what to do next, what to do even better than anything that can be done today. He says a lot about AI, actually, but he doesn't say enough about the information that we need to provide to the AI in order to allow the AI to design our next steps.
He was using a lot of stem cells, isn't he?
I think he's doing stem cells and exosome interventions. Yeah, I don't remember the details.
A while back, I had an interview with Max Moore, who I know you know, and he's been involved with transhumanism, and he's a real advocate for cryonics. And I know that you are also in favor of cryonics, and you're in favor of more research on cryonics. And in fact, there may be some, I know there are some members of this particular podcast audience that have a particular interest in cryonics. Could you explain your feelings about that?
Sure, yeah. I mean, cryonics is a criminally underfunded research area in medicine. Because basically it's got a huge potential to save a huge number of lives. And that potential is not being realized because research is far too slow. Cryonics involves taking someone who has just been declared legally dead, but who is only slightly more damaged than someone who has not yet been declared legally dead, and stopping that damage from continuing to accumulate at the much more rapid rate that occurs when somebody's heart has stopped than how it was going beforehand. And the idea, of course, is to stop that damage from accumulating by taking this person down to a very, very, very low temperature, typically liquid nitrogen temperature, when all chemistry stops, which means that all decay stops. And, this has been going on since the 1970s. And, that's certainly, good, but not nearly enough people have been cryopreserved. This should be a mass market thing. A huge part of why it's not a mass market thing is because at the moment, the methods that we have for doing this, for cryopreserving people, introduce a whole bunch of additional damage into the body over and above the damage that, caused their heart to stop in the first place, caused them to be declared legally dead. And the research that's necessary is research to fix that, to dramatically reduce the amount of damage that is done. At the moment, even though the amount of damage that is done is a lot less than it was 40 or 50 years ago, as a result of the development of a concept called vitrification, nevertheless, it's still a lot. Probably, honestly, too much to allow people to be revived by, warming them up and fixing up whatever damage they quote died of. So, of course, it's also possible to revive people in a different sense by essentially uploading them, by essentially slicing and scanning their brains and figuring out at very high resolution, what their memories and personalities were, and then building essentially an avatar. And for some people, that's good enough, which is why people who were cryopreserved poorly a long time ago are still not just allowed to melt and be buried or cremated. But of course, a lot of us, including myself, would very much not think of that as actual revival and reanimation, and that the only thing that would be actual, reviving somebody by warming them up and fixing whatever they died of. And that really is a very tall order, even with arbitrarily advanced future medicine, given the amount of damage that the cryopreservation process introduces. So this is what we need to do. We need more research. There are certainly a number of very promising directions for that research right now. More research that greatly reduces the amount of damage done so that reviving someone by warming them up becomes a much more plausible and feasible concept.
And vitrification is not really freezing. It's sort of like creating a glass-like state. Isn't that right? Something like that?
That's exactly right. Yes, that's where the word comes from, in fact. So glass is a solid, but it's what's often called an amorphous solid. So there's no crystals in it. And if you don't do that, then of course, when you take any biological sample which has a lot of water in it down below freezing, it forms ice crystals. It turns out that process of forming ice crystals is the source of nearly all of the additional damage. So if you can stop that from happening, which is what vitrification does, then the amount of damage that is done is a small fraction of what is done if you don't do this vitrification. However, even though it's a small fraction, it's still quite enough to be a real problem.
And part of your strategy involves replacement. Isn't that true? Replacement of organs.
Well, kind of. So, of course, we have today a whole branch of medicine that involves transplanting organs from organ donors. And It works okay, but a big problem with it is supply and demand, because in order to make it work, you have to find a donor who is very close to the recipient immunologically, and they don't come along very often. So huge numbers of people who are eligible for an organ transplant just don't get one, and they die on waiting lists. One of the huge applications for improvements in cryopreservation outside of cryonics is organ cryopreservation, to be able to take organs and bank them at these low temperatures for as long as you like until they are useful. In other words, until some recipient comes along who needs an organ and who is immunologically matched. Yeah, absolutely. And the reason that this is relevant to my work is because when we develop these rejuvenation therapies, rejuvenation is a very complicated, multi-pronged, divide and conquer approach to combating aging and increasing healthy lifespan. And some of those components, some of those technologies will be much easier to develop than others. So we're quite likely, I believe, to get into a transitional, temporary position where we can get to longevity escape velocity. We can get those 20 years, but only by doing things, some of which involve organ transplantation, some of which involve actually, doing surgery rather than doing injections. And, those organs may not come from donors. They may be grown in the laboratory, and that's fine. But the point is, surgery is inconvenient. Surgery is invasive. It's dangerous. So that's why I'm very sure that this will be a short-term measure, that people will work really, really hard to improve what we can do non-invasively, just with injections and so on, so that surgery ceases to be needed.
Yeah. So how far away do you think from actually being able to grow organs for ourselves?
We're getting pretty close, actually. There's a variety of ways of going about that. Some of those methods already work for some organs. The main problem that's always existed in this whole field of research, which is usually called tissue engineering, is vascularization, the creation of an adequate vasculature, so that blood can get around and provide nutrients and, of course, oxygen to cells at a natural rate, so that the cells don't suffocate and die. So there are various new techniques that have been developed over the past 15 or so years to improve that. One of them is what's called organ printing. Another one is what's called decellularization. But still, these things are, there's still some way to go before they really work as well as we need them to.
It's good to know. I think that's probably a very valuable area of research. But let's get into something a little bit more related to the politics and the business of aging and finding cures for aging. I've heard you talk about the FDA and NIH, et cetera, and how new drugs really are not, and anyone who's looking to create a drug that's going to, or multiple drugs that are going to cure aging, generally will not get funded because of the goal. The goal is too broad. I think you mentioned at one point, and also there are some drugs that are very effective today in terms of aging, but they're in public domain, and consequently there's no incentive to actually bring them out again.
So, well, first of all, of course, the last part of what you said is definitely not true, literally. There is definitely nothing out there that is very effective against aging. There are things that are minimally effective, maybe might give a little bit of benefit, but that's all. And that's why people like me are doing what we're doing, to try to make things that are much better. But the regulatory side of things, well, it's not quite the way you've said it. There is perceived to be a huge regulatory barrier to the development and introduction and testing of therapies that really work against aging, even in the future when such therapies are ultimately developed. And that's true, but it's not nearly as true as it used to be. One thing that I want to disabuse you and your audience of is the idea that the FDA are the problem, the Food and Drug Administration. They're the body in the US that, of course, approves clinical trials and approves drugs after they have passed through clinical trials. But they're not the problem. They just want drugs that work, and they understand that the health problems of late life, whether we call them aging or not, are fair game. That it would be good to have things that work. Furthermore, they understand that it would be good to have things that are preventative, in other words, that are given to people who are not yet sick and stop them from getting sick, rather than only treating people who are sick. People misunderstand that because they think, well, there's a bit of a revolving door between the FDA and Big Pharma, and Big Pharma make their money from keeping sick people alive and buying really expensive medicines, rather than from stopping people from getting sick in the first place. But that's not the Big Pharma's fault either. The Big Pharma will follow the money. They will make and sell anything that the public will buy. So the real problem is the public. The public are irrationally risk averse and do not really believe in preventative medicine. They believe in prevention. They're happy to agree with the idea that prevention is better than cure in principle, in the abstract. But the idea of medicine is inherently it's experimental. And therefore the risk of being healthy and taking something that makes you sick is central to their minds. However minuscule that risk may be relative to the risk of getting sick soon, and postponing the opportunity of postponing how soon you get sick using this medicine. This is a very, very difficult thing to fix. The inherent, irrational, disproportionate aversion that society has to preventative medicine. But coming back to the FDA for a moment, you mentioned breadth, and this is critical. What is necessary is the development of medicines that are both preventative and broad in their benefits, in the range of age-related, progressive, chronic conditions that they ameliorate or postpone. And that has already been done. About 10 years ago, a number of prominent gerontologists devised and went to the FDA with a proposed clinical trial for a drug named metformin, which is way off patent. It's been used against diabetes for decades and decades, but there was evidence that it might have much broader benefits than just diabetes. And so they wanted to try it. And the clinical trial was going to cost a lot of money because it would be a phase 3 trial with lots of patients. But first of all, they had to get FDA approval for the trial. In other words, they had to get the FDA to say, yes, if you do this trial and it meets its clinical endpoint, then we will approve metformin for that clinical endpoint. And the clinical endpoint was defined to be preventative and broad. In other words, basically it was a bunch of different individual problems of late life, whether it's cognitive or physical or whatever. And the idea was you had to postpone these things. The patients would be people who did not yet have any of those endpoints, and that you had to postpone more than one of them. So that was where the breadth came in. So, we've got now FDA approval for a form of words that does not use the word aging, and it may sound a bit convoluted, but the fact is it works. It's aging in all but name. And that same clinical endpoint, that same form of words can be copied and pasted into any other clinical trial that any big pharma company may do in the future for something that they do have a patent on. So that's where things will go. The regulatory regime is not really a big part of the problem right now.
Interesting. I want to get into your research. I know you just completed a very extensive experiment, or basically a series of experiments with mice. Could you talk about that a little bit?
Right. So, this was the last slide I wanted to put up with regard to the background. And it really underpins how reasonable it is to be optimistic about timeframes now. We are moving forward really rapidly. Not only are the original approaches to damage repair that I put forward 25 years ago being pursued really successfully, so that they're now in the private sector, but also alternative fixes keep emerging. So, we've got this thing called partial reprogramming, which is kind of an alternative to stem cell therapy. It's a way of essentially making the resident cells, the cells that are already in the body, behave in a more stem-like way than they previously were, which amounts to the same thing in many cases. Again, I could go down the list, but in the interest of time, I won't do so. The point is, as you can see, everything's got multiple approaches now. So here we have a description of what we've been doing at my latest organization, LEV Foundation, over the past couple of years. If we come back to this whole approach and we look at it, from 40,000 feet, this is a divide and conquer approach. It's an approach in which we're going to do a lot of different things to the same people at the same time. And any divide and conquer approach in any field of engineering has two phases to it. You've got to develop the components, and then you've got to put them together. Now, in non-medical engineering, the second part, putting them together, is generally the easy part. If the bits work, then you can be pretty sure that when you put them together, the overall thing is going to work. But in medicine, it's not like that, because we are seeking to manipulate a system that we have a really, really poor understanding of. So you could get lots of surprises when you do the combining, which means that I've been desperate to get to the point of starting to combine things as soon as possible. And this was our first chance to do that in earnest. We took 4 different treatments, each of which individually have been demonstrated to have benefits on mouse lifespan, even when they are used late in life, so starting in middle age. And nobody had put them all together. So that's what we decided to do, to see whether there would be an additive effect. It was a very big experiment, 1,000 mice, because we had to have 10 treatment groups in order to get all the information we wanted about interactions between the different interventions, making sure that we did the interventions correctly and so on. And we also measured a lot of things in terms of the health of the mice, visual things like loss of hair or curvature of the spine. These are things that mice get increasingly throughout their adult life. And behavioral things, you can test memory, you can test strength, you can test agility, you can test blindness, deafness. These are very well-established protocols that have been used by many research groups for decades. So we were able to leverage all of that. Some of what we did involved killing some of the mice at certain points, or indeed just collecting tissues from mice that died naturally, so that we could analyze them in a way that you can't do non-invasively. And that's still very much ongoing. So we also introduced an innovation with regard to what ages we did these analyses at. Essentially, I realized that there was a kind of trick being missed in other people's experiments when they were ordaining particular ages at which to do these things across the whole of an experiment. It's better to wait until a certain proportion of the mice have died in each of the groups individually, and then do these things. You get a better signal-to-noise ratio, essentially. So here are the results. First of all, I'm showing you for the female mice. So as I said, we've got 10 treatment groups. Here they are. And let me just draw your attention to the overall message here. The thick red line at the top is the mice that got all of these treatments. And the thick blue line at the bottom is the mice that got none of the treatments. So what these curves are showing is survival. So in other words, the x-axis is age, starting at the age at which we started the experiment, which was 19 months. And the y-axis is simply the percentage of mice that are still alive at any given age. So, of course, the curves always step down and to the right. And as you can see, the 8 other groups that got some but not all of the interventions are all somewhere in the middle. So this is very much what we wanted. We saw that if you have more interventions, then you have a greater increase in longevity. And of course, we want to do more of that. On the next slide. The males, so it's basically the same story. There are some complications here that we definitely don't understand fully yet. There are a couple of groups you can see that during the first year of the experiment, they did a lot worse than the control mice, the thick blue line. But then they caught up and they actually overtook the controls in the end. Similarly, there's a couple of groups that did perfectly well for the first year, and then they fell off a cliff, and the last mice died a lot younger than the control mice. So again, we don't understand that yet, but we'll be looking into it. So, of course, we want to do more of this. One thing that we have firmly concluded from this work is that we need to do more things at the same time. In the first experiment that we just concluded, we did 4 things to these mice. We believe that we want to go up to 8. The formatting's gone a bit out of whack here, but essentially there are maybe 10 things listed here, or 12. The first 8 are the ones that we're currently thinking of introducing in the next study. But as you can see, this is expensive. The next study will be twice the size, 2,000 mice. It won't be twice the cost because we've been able to find some cost savings. The previous study was $3.5 million. And so this one's definitely going to be in the region of $5 to $6 million. And it's hell on wheels raising that money, but I'm doing my best.
Just interrupt just briefly. You actually look for philanthropists for this research, correct?
That is correct, yes. One thing that unfortunately holds this work back is that it doesn't generate any significant new intellectual property. So I can't go to an investor and say, you know, if you give me some money, then there's a chance that you'll get a lot of money back in the future through owning something that's valuable. What I can, however, say to investors is that if you are already investing elsewhere in the longevity movement, so you already decided it's a good bet, and you are hoping for a return on your investment, then you have to ask yourself, you know, how big will that return be and how soon will it happen? And the answers to those questions depend on the rate of progress and growth of the whole field, including the kind of work that we're doing. So basically, one can view a donation to my foundation that hastens the performing of these experiments as a way to float all boats, essentially, to get results that will make people more enthusiastic about the industry overall, and therefore will increase the value of all companies in this space, even though LEV Foundation is a nonprofit.
Let's assume you achieve longevity escape velocity. What challenges do you foresee in terms of ethics, politics, and religion?
I really don't see any challenges at all. Fact is, you know, the kinds of things that have happened in the past that have had those kinds of conversations around them before they happened, we've seen what happens. The conversations just evaporate as soon as the thing comes along, whether it's test tube babies, whether it's organ transplantation. You know, it's just nonsense to suppose that there's actually any ethical issues here. People do not want to get sick. Nobody is ever going to want to get sick. Therefore, ways to help people not to get sick, especially not to get sick when they were born a long time ago, are not going to face any ethical quandaries at all. There may be changes to society that result from having a large number of chronologically old people, but no biologically old people. And of course, there will be a lot of changes to society that will happen earlier than that as a result of other progress in technology, whether it's automation or, the fixing of climate change, things like that. But honestly, the idea that there's any kind of ethical argument about keeping people healthy is just nonsense.
Good. Well, you helped design, or you were instrumental in designing the X Prize for Health Span. What do you hope to achieve with that?
So the X Prize, the X Prizes over the past 30 years, 25 years, have been unbelievably influential in accelerating really ambitious cutting-edge technology in all walks of life. And I'm privileged that Peter Diamandis and I have been good friends for that whole time, pretty much. And certainly we've been talking about doing some kind of longevity X Prize for at least 15 years. But honestly, the science wasn't there yet. Peter's success with the X Prizes has arisen from the fact that he has an extraordinarily good instinct for when the time is right, when there is a kind of sweet spot between, being too easy and being too hard. He looks for essentially a combination of audacity and achievability. And so 6 or so years ago, the time started to be right. it became possible to take what was already possible, what was already known in this field, and to design a prize around that involved rejuvenating people and therefore developing technologies that could be widely used. Took a while for it to come together. It didn't really come together fully until last year, but it's very much rolling at the moment. It has the backing of most of, if not nearly all, really, of the luminaries in the field. I'm very happy with how it's turned out. Certainly, as you say, I was heavily involved in the design, especially in the early stages of it. And I'm still very much involved on the scientific advisory board. I have hope that it will succeed. The stated goal of the prize is to take people who are already in middle age or older and to treat them in whatever way you want to for a maximum period of a year, and to derive from that treatment a at least 10-year reduction, not just slowing, but reduction in biological age, as measured through various types of function: muscle function, cognitive function, immune function. If you get 20 years, you get even more money, but you have to get 10 years to get any money.
You're one of the few people that actually puts a time frame on this. You predicted that longevity escape velocity will happen by around the late 2030s. What must go right in the next 10 to 15 years to actually reach that?
Yeah, absolutely. So, of course, I always put a probability on it. I say that I think we have a 50-50 chance of reaching longevity escape velocity within the next 12 to 15 years. So, as you say, the late 2030s. The main thing that has to go right is the first thing. We need to make sufficient progress in the laboratory that the experts in the field, the subject matter experts, feel that they have, if you like, permission to go out and do the same as me, talk about actual timeframes. At the moment, it's not just that I talk about one time frame and other people talk about different time frames. I'm pretty much the only person who talks about any time frames at all. And that has to change. I'm absolutely certain that is the kiss of death for the credibility of the subject matter experts. If they're not willing to put their reputation on the line and say, I think we have, this amount of progress in this amount of time, with this probability, then nobody's going to believe them. They're just going to be seen to be just trying to, attract more funding for the research that they happen to enjoy doing.
Well, this has been absolutely fascinating, and I think that if there's any breakthroughs in aging, it's going to probably happen through you. Let me ask you one question in closing. If someone listening is skeptical but open-minded, what's the one belief about aging you'd most want them to reconsider? Well, of course, that rather depends on why they are skeptical. If you're talking specifically about skepticism as regards the feasibility of all of this, and if we basically are talking about people who are not fooled into believing that aging is any kind of blessing in disguise, then I would say the main thing to look at is simply the main thing to instill in people is the understanding that the analogy with simple man-made machines like cars really is a valid analogy, that the body is a machine, which means that its function, including its longevity, is determined by its structure. And therefore, that restoration of structure, which is what preventative maintenance is, will confer restoration and rejuvenation of function, both mental function and physical function. If one gets that, then one is most of the way towards understanding that this is abundantly feasible. Fantastic. Aubrey, I really appreciate you spending the time with our podcast audience. I'm sure there are a lot of questions that remain, and we're sending out an email with a questionnaire, and we'll be getting additional questions from them, and I'll pass them on to you, and hopefully you'll be able to answer them. I would be pleased to. Thank you so much for having me on the show. Thank you. I want to tell you a little bit about purposefulbuying.org. It's entirely managed by our smart capstone students. The platform sells Nepalese products, with all proceeds going to Pahar Trust, a 30-year-old charity that's building schools in many of the most remote villages in Nepal. Check out purposefulbuying.org. Our next guest, Natalie Pace, will be joining us on May 8th. She's a financial educator, author, and sustainability advocate known for her data-driven approach to personal finance and investing. She's the co-author of the ABC investment strategy, which emphasizes diversification, risk reduction, and sustainable asset allocation. Natalie is the author of multiple books, including The Gratitude Game, The ABCs of Money, and has been featured in Forbes, Bloomberg, and the Huffington Post. A strong advocate for financial literacy, she focuses on empowering individuals, especially women, and younger generations to take charge of their financial lives in an age of volatility and rapid change. In closing, I want to thank our podcast audience and let you know that each of you will be receiving an email that includes a brief survey. Please take a few minutes to fill it out. It helps us improve these podcasts for the future. I want to thank Dr. Aubrey de Grey once again for spending time with us today, and I want to thank you all for joining us on the Westcliff University podcast. Goodbye.